Hey everyone, we're back. In this episode, I talked to Jessie Yeung. She teaches a course about probabilities. And in this episode, we talk all about probabilities, sampling, bias, and why the house always wins. I hope you enjoyed this conversation as much as I did, and see you on the other side. Okay, great.
All right.
Yeah, election, gambling.
We'll talk about surveys, bias.
What do you think about what do you think about like recent election polls? Do you think it really reflected the results?
So I think that when we think about election polls, we have to really remember what exactly the election polls are trying to measure, right? So a lot of people think that with an election poll, they're trying to predict what's going to happen in the future on election day. But that's not exactly what polls are trying to measure. Polls are simply trying to estimate how everyone would respond to the polling question on the day of the poll if they could ask the poll to everyone.
Mm-hmm.
So it's a bit different than predicting the future. The polls are just trying to evaluate what's going on right now in the present. So if you have a poll that's 2 weeks out from an election, it's measuring something that seems to be like they're guessing what's going to happen in the election, but not quite, right? Because that element of time can change things. There's people who might estimate, who might respond in a poll, but they might not actually go to the actually vote in an election. Or there might be people that aren't really accessible through the poll, but then they actually go to vote in the election, right? So I think that we have to be really careful about what exactly the polls are trying to measure, and remember that it's definitely possible that polls are wrong, but just because the poll doesn't match with the election results, it doesn't necessarily mean that the poll was wrong, because things could have changed in the meantime.
So I think you're speaking to something you would call bias in these pollings, right? So I mean, specifically about this problem of like election polling, what are the biases? Well, I mean, first of all, like people who respond to these surveys are like, I don't know, a certain type of people.
Yeah. So bias could exist anytime when the group of people that we've polled don't represent the larger population that we want to estimate this for. So it could be the situation where certain groups of people just aren't available to answer the poll, right? If you do a poll through texting people on their cell phone, there's a segment of the population that won't respond to text messages. They don't know how to respond to text messages, or they don't have cell phones, right? You could also have bias because the question that you're asking isn't being interpreted the way that you think it is, right? So people might give you a different response than you'd expect. You also have a level of social desirability, right? People might give you the answer that they think is more socially desirable, that they think maybe you want to hear, that is more socially acceptable, instead of giving you the answer that's their actual truth, right? So you have all these different sources, and all of those can lead to bias.
So you teach a course here, Probabilities Everywhere. What's up with the name? What does it imply?
So the course actually predates my time teaching at U of T at all. So technically, I did not come up with the name, but I do think that it's a good name that encapsulates what we're trying to do with the course. So the idea is this, right? You go through your everyday life, and you're always encountering uncertainty in so many different facets of your life, right? It could be something simple like, is it going to rain during my afternoon walk? Is my favorite brand of cereal going to be on sale this week at the grocery store? Or, is my manager going to call in sick today, right? So there's all these different sources of uncertainty. And the goal with this course is we're trying to help people make sense of all of this uncertainty, how to quantify this uncertainty through probability, And my what I'm trying to show people is that when you do that, when you try to make sense and quantify this uncertainty, it actually helps you understand the world a bit better and also helps you make better decisions as well.
So fundamentally, it's like a different way of thinking, maybe perhaps like probabilistic thinking.
Yeah. So if we're not used to going through life thinking about things and analyzing probabilities in a certain way, then, we're not used to it. We won't do it. But what I hope to do through this course is, uncover a different way of thinking about uncertainty. And hopefully that helps us become more critical about things that we perceive and helps us with our day-to-day lives.
And I think that's like the main value of this course because it's not like a math heavy, like formulas first course. It's more about like real life applications and case studies, right? Um, I'm wondering what are some of the case studies and like applications of probability that you teach in this course?
So we'll talk a lot about election polling,
Mm-hmm.
right? Because that's very relevant. We during election times we see a lot of polls in the media, on social media, so that's particularly relevant. We'll also talk about gambling bets that you may make at the casino, buying a lottery ticket, sports betting, things like that. And we also want to be critical and understand bias in many different facets of our life, right? We think about bias in terms of surveys, polls, but bias can exist in other areas that we don't necessarily think about as well. And so it's just about learning about those and recognizing where those things might exist.
Interesting. So let's talk about election polling since I think it's very timely. What surprises the most, like students who will learn about this in this like specific framing that you're teaching?
So I think that the biggest misunderstanding with polls is exactly what the polls are trying to measure, right? So a lot of people, they see a poll and they think that the poll is a projection into the future. It's this magic crystal ball where you're looking into the future and you're guessing who's going to win the election, right? Whereas polls are not exactly trying to guess what's going to happen in the future. Polls are just going to evaluate what's going on in the present. And so to be more specific about it, polls are trying to determine, if we were to ask everyone in our population of interest this polling question on the date of this poll, we want to estimate what everyone in the population would respond with. So it's not a projection of the future, it's a snapshot of what's going on in the present. And there's a distinction there, right? And so those two things are not exactly the same thing. One's a prediction of the future, one is looking at what's happening in the present. And so when you are receiving information about a poll, it's really important that you make that distinction. And so in order to make sure that you don't make erroneous conclusions about what you see.
Mm-hmm. I guess we have to talk about the problem of sampling to really understand what's happening here in terms of like all these biases you mentioned. Do you know like how do these like research firms go about selecting specific people that they contact to ask these questions?
So in probability and statistics, the best way that you choose a sample is through some sort of random process, right? Because we presume that if we're able to choose our sample in a random way, that's going to help our sample be representative of the population. And that's the key, right? We want our sample to be representative of the larger population. And so they could go through different techniques. Typically, these organizations that are running these polls or these surveys, they'll have some sort of database that they can choose from. Maybe it's phone numbers, and they're going to call or text these phone numbers, right? So they have access to some list which serves as a proxy of the list of everyone in the population. And then what they'll do is they'll use different techniques to randomly choose people off of that list. And that's typically how people will choose who ends up being in their sample.
Yeah, but like as you said, I think it could be still very biased because like you're targeting people based on having phone numbers and like replying to your
Mm-hmm.
phone or text. Um, but I mean, I don't know. We can talk about biases and stuff, but at the end of the day, these like polls seem to be very accurate in terms of like reflection of the actual results. So I think like I don't know how they're doing it, but they have a I don't know secret
They have
sauce
some
or
magic.
something that can like yeah, because I mean sometimes they get it wrong because as you said things change over like the past I don't know few days leading to election, but it looks like they have like a structure system in place that they can consistently I don't know do these things like every now and then.
Yeah, so the thing with bias is that if you're anticipating it or if you know of a specific kind of bias that may exist, there's things that you can do to adjust for. So for example, if your sample that you've collected skews younger, you can make an adjustment for that by putting different weights on different people's responses. So the few older people you have in your sample, you can put a higher weight on them and then reduce the weight of the younger people just so that you've evened out the effect and it's more representative of the larger population. So as long as it's something that you anticipate, there's a lot of things that you could do before the survey or during the analysis of the survey in order to adjust for that.
Mm-hmm. So let me ask you this. What does the margin of error actually mean? And what are the most common ways people misinterpret this margin of error when reading polls?
So when you are trying to estimate something for a population, the margin of error is really just telling you a the degree of uncertainty related to that estimate. So let's say that you have this really simple poll, and the polling question is, do you support candidate A? Okay, so people will answer yes or no. And we're interested in the percentage of people that support candidate A. Okay, so maybe the poll comes back and in the result it says 60% of people support candidate A, and there is a margin of error associated with that of, let's say, 5%. Okay, so you have 60% and then you have your 5% margin of error. What you could do is you could combine those two things and you could create an interval. And so we would create an interval of 55% to 65%. We take my estimate and I plus or minus my margin of error. So now we've created this interval where we are fairly confident that the true percentage of people that support candidate A is somewhere within this interval of 55 to 65%. And with this interval, typically the way that the margin of errors are calculated, we would have what we call 95% confidence. So we're 95% confident that the truth lies somewhere in this interval. There's still a chance that we're outside of the interval, though, right? There's still about a 5% chance that we're outside of the interval. But my margin of error is essentially telling me, how far away I can expect to veer away from that 60% estimate. Okay, so a margin of error is just telling you how good of an estimate do I have here? Is this something I can really trust? Do I think we're close to the 60%? Or do I have a lot of uncertainty around the 60% measure?
So how can I reduce the margin of error?
So there's lots of things you could do. One of the easiest would be to sample more people. So the more data you collect, the better you feel about your results, the better you feel about your estimate. And then all of a sudden, your margin of error is going to be smaller and smaller. So that's the main way that people like to think of in order to reduce the margin of error. There's other more statistically sophisticated ways, different techniques of sampling, things like that. But changing a sample size is probably one of the most intuitive ways.
And in your course, you also talk about the magic of number 1000 when it comes to sampling. Can you unpack that?
Yeah, so the point here is that whenever you look at surveys, polls, anything like that, if you look at the sample size, the number of people that they've collected information from, you often find that the sample size is going to be close to 1,000. And that's because at 1,000, people have generally accepted the associated margin of error to be small enough. So let's say, going back to the example of we want to estimate the percentage of people who support candidate A. If you have a representative sample of 1,000 people, your margin of error is going to be 3%. And generally, 3% of a margin of error, people are thinking that's a decent amount of accuracy that I have, right? We feel good about that. So that's why a lot of people in the polls, they hit around 1,000. 1,000, we have about a 3% margin of error. We feel good about that. So that's why typically the sample size ends up being somewhere in that neighborhood.
And is it just for the context of election polling or in general?
In general. So the margin of error is not going to be in a percentage all the time, but in the context of whatever you're trying to measure, you have to decide at that point, what margin of error are you typically comfortable with, and so that's gonna change, what sample size you're interested in collecting for.
Interesting. So you're saying people go backward, they start with the margin of error that they're comfortable with, and then they work backward to estimate the number of samples that they need to collect.
Yeah, and that's actually a very common practice. It's actually aptly called sample size calculations, where you take the margin of error you're comfortable with, and a few other pieces of information. You have to predict what your results are going to be. You have to predict how much variability you expect to have in your results. But you take all that information and you can actually derive these formulas that will tell you, okay, if you want that much accuracy, this is how much you need in terms of your sample size.
Does that prediction part come from previous data, or you just have to really guess it?
The prediction part is the trickiest part of the sample size calculation. So if there are previous research available, typically you'll pull from that. If you're doing something completely novel, you do have to guess. And so people do call into question how good sample size calculations are. But a lot of times, if you're not sure, you might just increase it a little bit to try to be as safe as possible.
And this sample size calculation, you're saying, is it just one standard formula that everyone uses, or depending on your industry or I don't know, use case, you just have different formats and formulas?
They're very different, and it depends on the type of statistical analysis that you want to run, and it depends on the format of your data. But they do get quite complicated depending on your specific situation. And so that's why it's helpful a lot of times to get a statistician to help you with dealing with this type of thing.
Interesting. So format of data as well. Yeah, but let me go back to this thing you mentioned, 3% as a good margin of error. So what is a good margin of error? What do you consider to be a good margin of error? Do we have a standard number or something 1%?
We don't have a good standard measure of what's good enough. For election polling, it does seem to be about 3% is what people are generally comfortable with. But it really depends on your specific situation. How accurate do you need to be, right? What are you using this data for? What are the conclusions going to be used for? Is it going to be used for something that's very critical, something that's life or death? Then you want more accuracy, right? If it's not that serious, then perhaps you're okay with a larger margin of error, especially if it's more of a preliminary study. Take the smaller sample size, do it quickly, and then see what the results are.
Let's also talk about gambling.
Hmm.
So there's a saying that the house always wins.
Yes.
Can you elaborate on that?
Yeah. So in order to dive into that, I think we should take a step back and talk about this concept that we have in probability and statistics called the law of large numbers. Okay, so law of large numbers, it's this big theorem that we have in probability and statistics. And it basically says that if you have an experiment and you repeat this experiment over and over and over and over again, if you were to average or aggregate the results from all those experiments, the more experiments you run, the closer your average is going to be to the expected result.
Mm-hmm.
So, for example, if you're flipping a fair coin, right? And if you're flipping a fair coin, you would expect that 50% of those coin flips would land on heads.
Mm-hmm.
Let's say you flip a coin 10 times, right? And let's say of those 10 coins, 7 of them land on heads. So with your 10 coin flips, you have 70% heads. Okay, 70% heads, that's a ways away from 50%. But that's because you've only flipped the coin 10 times. Now imagine you flipped it over and over and over and over again, and let's say you flipped it 1,000 times. Once you flipped it 1,000 times, it's going to be really unlikely that you still have 70% heads, right? Once you haven't flipped it that many times, probably you're going to be very close to 50% heads. So the more you repeat something, the closer you are to the expected amount. So this applies to the casinos because a casino is going to receive thousands of bets every single day, right? And so because they receive such a large number of bets, that means that the law of large numbers is at play. And on average, for every bet, they are going to win/lose the expected amount, whatever that is. It's the mathematically expected amount for every type of bet that they have. Now, so that's the first component, the law of large numbers. We have a lot of bets in the casinos. The second component to that is that every bet that you make at a casino slightly favors the casino, not the person that's gambling, right? So if you go to a casino and you place a bet, you are incurring an expected loss of probably a few cents for every time you bet. Okay, so every time you bet, it's an expected loss and an expected gain for the casino then. And so you take that and you combine it with the law of large numbers. This means that at the end of the day, when the casino has received thousands and thousands of bets, with the law of large numbers and with the fact that they're expected to win a few cents on every bet, they're more or less virtually guaranteed to have an expected profit of a few cents for every single bet that someone has placed at that casino. So you combine both of those things together, and the casino's in a good position to earn money from all of the bets that have been placed.
Mm-hmm. So the more people come into the casino, it is more likely that they make more money.
Yeah, as long as a large number of people are placing, or as long as a large number of bets are being placed, the casino is guaranteed to make an average of a few cents for every bet, essentially.
Mm-hmm. You hear a lot that people say lottery is a scam. What do you think of that? Because, I mean, like, I don't know, statistically, yes, like your chances are very low, but at the end of the day, somebody wins. So,
but that person won't be you.
okay, yeah.
So lotteries, like the casino bets, also have an expected loss. So every time you are paying money for a lottery ticket, you actually expect to lose a few dollars. Okay, so some people are going to win. A handful of people are going to win big. But most people are going to lose the money that they paid for the lottery ticket. So if you average out everyone's results, the new millionaires and then all the people that lost a few dollars, it averages out to everyone losing a little bit of money.
So if I'm understanding correctly, the magic behind 1000 is just the law of large numbers,
Um, n-
or they're
not,
completely different.
not quite,
Okay.
not quite.
Um, tell us the story of the lottery that was actually worth playing.
Yeah, the lottery that's worth playing. Yeah.
Mm.
So when so this is a story that goes back to 2004 in the state of Massachusetts. And at the time, the state was running a particular lottery that had grown a bit stale. Like, people weren't really interested in it. They weren't producing a lot of winners. And that meant that people weren't really buying any lottery tickets. Like, sales were low. Because if you have a winner, that's marketing for them, right? You advertise, okay, like this person won, they were close to your city, and that's what drives sales for lotteries. So they had this lottery, people weren't really winning, so they wanted to replace it with something else that was strategically going to produce more winners. So what they did is they created this new lottery. It was called Cash Windfall. And the way that it worked is that if the jackpot were to hit a certain number and no one had won the big jackpot, they would take the jackpot and they would split it into different parts, and the money would essentially roll down to people that did not match all of the numbers but still matched most of the numbers. Okay, so you take that jackpot and you roll it down to other people, thereby producing a lot more winners. So remember that lotteries typically produce an expected loss, right? On these specific roll down days where this would happen, the lottery actually had an expected profit, even after accounting for the amount of money you have to pay for the ticket. Okay, so on those specific days where it would roll down, there was an expected profit of $3.50, roughly. Okay, now if you went to buy one lottery ticket, you would probably still lose. But if you bought many, many, many tickets, because of the law of large numbers, on average, you should profit that $3.50 for every ticket that you get. So all of this was discovered by this man named James Harvey. He was an undergraduate student at MIT at the time, and he was doing his project on lotteries, and that's when he did all these calculations and figured this out. So what he did was he gathered a group of his friends, and they pooled all their money together, and they bought 1,000 tickets. And you had to specifically do this on these roll down days. And what happened was it worked. They made money from the lottery, right? And so over the course of the several years where this lottery existed, they kept doing it on these roll down days, and they actually ended up making a lot of money by doing so. There were other groups of people that figured out similar things, and they were doing it too. But in the end, James Harvey and his friends ended up making an estimated few $1 million by doing this.
What happened next? They just canceled the lottery? And
Eventually they did, but it wasn't immediately after they discovered that people were doing this, because if people were buying the tickets, that means sales were good, right? Sales were good, and so other people would buy the tickets on non-roll down days. It became a popular lottery, and I think that the state organization was making good money by doing that, right? It served the purpose of replacing the old lottery that was stale. So in a sense, the government did get what they had wanted to achieve too.
So how is it different from like today's lotteries? The expected profit is lower, or
So
what did they change?
So it's a rare situation that you would find a lottery with an expected profit. Typically, for any lottery that you see today, it's going to be an expected loss. So every time you buy it, you're going to incur a loss of a few dollars. So if you, in that case, if there was an expected loss and you bought 1,000 tickets, you would just expect to incur that loss over 1,000 times, right? So that wouldn't be a good deal.
Mm-hmm. Let me go back to my questions. Okay, I have one more question about sampling. Sampling seems like this dry statistical idea, but your course paints it as powerful. What's the superpower of sampling that people often overlook?
So sampling is great, right? Because we can learn about the characteristics of an entire population by only getting information from a much smaller group of people. So sampling is really powerful in that way. But the key is that your sample has to be representative of the population, right? So as long as you can ensure that, sampling is a really powerful tool. So before we were talking about how if you had a poll and you had a sample size of about 1,000, you'll get roughly a 3% margin of error, right? So let's say you're interested in doing a nationwide poll across Canada. If you have a representative sample of 1,000 people, you get that 3% margin of error. Okay. Let's say you were doing a nationwide poll in the US. If you have a representative sample of 1,000 people, you still get that 3% margin of error, even though the population of the US is almost 10 times that of Canada, right? And so the cool thing about sampling is that even if your population gets larger and larger and larger, you don't need to scale your sample size in the same manner, right? So I think that's one of the most powerful things about sampling.
Okay, so let's say my whole population size is 900, like something less than 1,000. What's the second best number? Do we have like another number like 100 or like just the more you can get?
So once your population size is as small as 900, the general rules don't really work in the same way because mathematically the formulas need some sort of correction to account for the fact that a population is so small. So most of the rules that we have, like 1,000 people, 3% margin of error, those apply when our population is just a much larger population. So if you had a smaller population, say 900 people, you could use the same formulas to calculate the margin of error, but the formula would just be slightly different. You would have some sort of finite population correction to do.
But I think it's very powerful what you said about even though like the population of I don't know, another country might be 10 times bigger, but you don't need to scale your own like operation.
Yeah.
If you think of it as a business, like I think that gives them such a great leverage that they don't need to like scale their whole operation. But I guess the challenge would be finding the right 1,000 people in another environment. And
the key really is you need the 1,000 people to be representative. So it's really powerful, but the difficult part is how do you access this 1,000 people that's going to be representative?
And I think you kind of implied this at the beginning, but so they definitely have more than 1,000 because they don't want to exhaust that list. And like, say they have like, I don't know, 20,000 people and like they just randomly sample 1,000 from that list every time. Because I mean, I assume if we just keep asking the same question from like the same people, they might get tired or like bored or just like they don't want to mess with you or something, you know?
Yeah, for election polls specifically, every time I think they'll ignore who they've asked in the past, and they'll just randomly choose 1,000 people again. There might be overlap. That could happen. But I think that every time that they'll just try to choose from the list, ignoring who they've chosen in the past.
And speaking of bias, there's a great story of Abraham Wald. Can you tell us that story?
Yeah, so this is a story that doesn't seem on the surface to have anything to do with bias, but actually has everything to do with bias. So Abraham Wald, he was this really famous and prominent mathematician and statistician. And during the Second World War, he lived in New York City, and he contributed to the war effort using math and statistics. So many times the U.S. military would go to Abraham Wald or his colleagues to ask them for help dealing with certain situations that they thought a mathematical or statistical lens could help with. So there's this really famous story of a situation where the military goes to Abraham Wald and asks him about his advice on what they think is an optimization problem. So the situation works like this. You have these American fighter jets that fly from the US to Europe to be used in combat. And of the planes that came back, they collected data on them. They looked at the planes and they wanted to see where those planes took the most damage. So they looked at the planes and they said, of the different sections of the plane, where do we have the highest number of bullet holes per square foot? Okay. So they looked at the different sections of the planes, and what they found was that the engine tended to have fewer bullet points per square foot. Bullet holes per square foot, whereas the rest of the plane area, such as like perhaps the wing, tend to have a higher number of bullet holes per square foot. And so they thought, this is a great situation for optimization. If we want to make our planes stronger, let's add a bit of armor to our planes, and let's add a bit of armor to the parts where it seemed to be a higher number of bullet holes, right? But they saw this as an optimization question because they want to put armor, but if you put too much armor, then it weighs your plane down, not as fuel efficient. So they went to Abraham Wald with this question. And so when Abraham Wald looked at this scenario, he didn't give them the answer that they had expected, because he recognized that there was a high amount of bias in the data that they collected. What they saw, what he said was that you shouldn't put the armor in the places where you see a lot of bullet holes. You should put the armor in the places where you do not see a lot of bullet holes. In this case, it was the engine. And he said that because he recognized that the data that they had collected was very biased. They only got data from the planes that came back from Europe, right? They did not get any data from the planes that were shot down on the battlefield and remained on the other side of the ocean.
Yeah.
Right? So there is a lot of bias in the data that we have. We can't make any measurements on the planes that were shot down, right? And so he said that, well, the reason why we don't really see many bullet holes on the engine is because if they were hitting the engine, there's a high chance that they weren't going to make it all the way back to the US. And so that's why he made the recommendation that he did. In this case, the population of interest is all the planes. The sample were only the planes that returned, and we're completely ignoring the planes that were shot down on the battlefields, right? And so you have the situation where the US military, who arguably has a lot more experience in aerial combat, wasn't able to see this inherent bias that was present. But Abraham Wald, who was a statistician, and statisticians are used to thinking about things in terms of, where is my data from? What kind of biases do I have, right? When you're used to thinking about that, it's a lot easier to recognize that you have a large amount of bias here. So that's the story of.
Did they take his recommendation?
They did.
Okay.
Yeah.
Good. But I mean, I don't know. That's still fascinating and kind of scary to think that like a big organization, like even like I don't know, U.S. Army, they have like such a big bias in conducting their operations. Um, okay, so let's go back to your course. From pools to poker, your course spans a lot of real world problems. How do you decide what topics to bring in, and what does that reveal about how probability works in the world?
So I try to bring in examples from a large number of I try to bring in examples from various fields of study so that there's something for everyone. And I also look at what are the things that we interact with in our day-to-day lives that relate to probability, that have a degree of uncertainty to them. And what I try to show the students in this course is that probability is very relevant in our everyday lives, right? With math-based courses, there tends to be this belief that outside of this course, outside the classroom, this stuff isn't relevant, right? I won't need to use this information when I get out of this course. But I try to show that that's not necessarily the case, right? If you look at things through a probability lens, there's a lot that you can learn from that.
So for you personally, what's one everyday situation that I think you think a lot about probability? Like your decision-making process is more like probabilistic.
So I think so I think what comes to mind because of the last few weeks is definitely the election polling, right? I think that there's a lot of people that like to trust the polls a lot if it's telling them what they like, or people that want to disregard the polls as much as they disregard the polls if it's showing them something that they don't like, right? And I try to be of the belief that, polls are only measuring, what the situation is today. It's not trying to predict what's going to happen to the election. In the election, theoretically, anything can happen. The polls can tell us what direction we may be going, right? But we have to remember that we have to still be prepared for anything that could happen on election day.
Yeah, that's true. What do you hope your students never see the same way again after taking your class?
So I hope that after going through the course, students don't think about uncertainty in the same way. So I hope that they don't see uncertainty as something that overwhelms them, that scares them, right? I want to show them that uncertainty is something that you can reason through. Uncertainty is something that you can work with, that you can analyze. And hopefully that makes them more confident in making decisions despite all of the ambiguity that we have.
But you're saying if I take your course, the message will be don't gamble at all. Like instead of just like here's a way how you can win the lottery or something.
Perhaps I do have a more cynical perspective of lotteries because of my knowledge of probability and statistics. I like to see lotteries as, if for you it is entertainment, then it's okay to spend money on entertainment within reason, right? But don't think that you can use the lottery or casino to become rich one day, because chances are that's not going to happen. And it also means that if you happen to get lucky in a casino early on, you should stop, because the more you play, the stronger the effect of the law of large numbers, and that means that you'll incur a loss on average.
Yeah. Great. Thank you so much.